Okay, that's great. Thank you, Sarah. Welcome to everybody. I'm just going to pause my webcam, just kick off with the presentation. Okay, so in terms of the agenda for today, this is the program for the first webinar for the year. So this is one of the user group sessions that we run. We have other ones that we call webinars that we run as well. So this is a kind of a number of little sort of bite-sized topics that we tend to cover with these, with a little bit more opportunity at the end for some Q&A as well. So the subjects we're going to look at today, so it's a combination of, as Sarah mentioned, of Ross and myself. I'm going to cover a little bit on just looking at coverage plots with some high resolution, in this case some Lidar data. So this is circa 1-2 meter high resolution surface model data. So I've got a little example area we've got with some coverage plots we'll generate. On the back of that, I'm also going to look at a way to do batch coverage plots actually. So this is a large number of stations that you might have within a network, and batch coverage plots with those. And then finally in my segment, we'll just look at ways of exporting. So having done some coverage predictions, then being able to take them out to view or do some further analysis. So we're going to look at KMZ and shapefile formats as terms of other formats to export coverage out into. I'll hand over to Ross, who's then going to cover a bit on population coverage analysis. So this is looking at some polygons and some population figures associated with those, and just interpreting coverage. And finally then he's going to just give a little introduction to the API. So it's got a fully functional API with Spectrum E, so just to introduce that. A number of you may not have seen that, and hopefully that will be of some use to a number of you guys out there. And as I say, we've got some time at the end for some Q&A, but if there is any kind of points of clarification, understanding, as Sarah mentioned, then if you just put those through the question toolbars, and I'll cover those as we go if it's sort of clarification, and if not, we'll park them towards the end. Okay, so I'm just going to bring up Spectrum E here. And I've got a little example area. So this is just an area in the UK, Eastern England. For those of you who know it, we're out over in East Anglia and in Norwich. And we've got some high resolution data for this. This is to say is actually originally freeware data, so it was freely available, let's call it. So this has been processed into the format that Spectrum E is going to use in a surface model, so it's captured from an aircraft that's picking up the Lidar. So this is the map image layer, just to give you an idea of the area of interest. And then I'm going to just zoom in a little bit and then just have a look at the data, and then we'll look at coverage predictions with that. Okay, so this is just the map image layer that I'm viewing in the moment. So under these display options, I'm just going to move over to the terrain view. Okay, so at the minute we're looking at this kind of medium resolution cartography that we have. So we have pretty much terrain data for the whole of the globe, circa 30 meter resolution. So very appropriate for sort of high level planning, and but obviously there are certain types of technologies and situations where you may want some higher resolution mapping data. And that's obviously where this Lidar data example would be preferable, perhaps in a number of cases, to give you a bit more certainty. Particularly in the case that I'm looking at here, it's going to be a fixed wireless access network, and it was particularly sensitive, let's say, to trees and similar obstructions of that. So not strictly a line of sight system, but something quite close to that, just with the frequencies that we're using. But I'll come on and show you the network in a moment. So I'm just zooming in to level 15. So this is just down this sort of bottom right-hand corner, there's this little information display. This tells me to be a bit about the position information at this little blue crosshair I have, but also the level that we're at. Okay, so it's just a series of levels of data, and at level 15, that's when we have this terrain data that kicks over to you can see the surface model data. So We've got a number of, you can see buildings, obviously trees and other foliage that you can see here. So this is what's called a surface model data. So what have been captured, and we'll pick up basically all the obstructions that are in the path when we're going to come on to do a coverage profile. So whether that's trees, buildings, etc. So this is at 2 meter resolution, the data we've got here, based on some of the original Environment Agency data that's available. There's a number of other data sets, similar data sets that are available perhaps freely around the world, or other agencies may have them that with purchase options as well. So this is becoming more prevalent, this type of Lidar data. Okay, so that's just a little bit about the data, as you can see here, just as an example, just zoomed into an area. So I'm just going to take you then to the network tab here. So I've just got a series of a small network number of stations here. So this is using sort of a fixed wireless access. So this is a 4 watt EIRP system that we've got here. So sort of medium size in terms of power. And this is at 5.8 gigahertz. So whilst not line of sight per se, then obviously we get quite sensitive to, you know, large obstructions, particularly trees and other buildings. So having this extra resolution rather than just a terrain layer and perhaps with a coarse clutter layer on top will give us a bit more certainty in terms of this coverage prediction. And I'll show you the coverage prediction that we're going to use with this high level, with high resolution rather, data. And I'll also just show you another one that was created using the medium resolution, just so you can kind of get a sense for the difference between the two and the extra detail on what that's giving us. Okay, so just to view one of these stations here. So I've just got a predominantly omnidirectional antenna pattern, as I say, sort of 4 watts with a 5.8 gigahertz. Now the antenna heights we've got for these are actually, because we're referencing a surface here in this Lidar model, then there's a mixture of antenna heights. So you can see this one 6.5 meters. So some of these effectively would be on the ground. You can see some of them here where it's saying 2 meters. So this is, you know, an antenna that would be located on the building. So it's above the height of that building in this case. So rather than having it, you know, 10 meters above the ground level. So just something to bear in mind when you've got these surface model data, that you don't, you know, then put an extra high antenna on top of the surface and perhaps over predict in terms of the coverage. Okay, so I'm just going to take just 3 of these initial stations and just run this path loss calculation. So this is kind of a 2-stage process to generate the coverage calculation. So the path loss is where the main computational stage is done. What we've got here is obviously just some input parameters. So this is just a receiver antenna. Again, this is referenced to the surface. In this case, it's a couple of meters above that. So similar to let's say a fixed wireless access service that we're looking at. The key bit here, other than obviously the 50% of time and locations, is this clutter option. And obviously, in this case, we're going to use what's called this high res. So this is taking account of this high resolution data that we've got. Okay, so obviously, depending on what data you have, then that may or may not be applicable in terms of the high res option. Okay, so this is, say, circa 2 meter data that we're looking at here. Just running it initially just for 3 stations out to a kilometers or 5 kilometer distance we got. So obviously it's a balance here with this range that you're doing and the resolution that you have. You can see that didn't take very long to do it for just a small number of stations. But obviously if you were starting to increase that range, then it's perhaps a balance between the range and the resolution that you've got with this type of data. Okay, so that was for those 3 stations, and then I'm just going to run the second part of it. So having run that path loss matrix, I'm going to look in this case at a downlink power received coverage. So I've selected my stations. In this case, say it was looking at a fixed wireless access network. So I'm going to include some receiver antenna gain in this. So this is a receiver antenna that would be situated on the external to a property. So it's a reasonably directional and obviously again reflects that. So I've run my initial path loss matrix calculation, and then the second stage is obviously this secondary bit, which looks then at these three stations in this case that we've got here. So you can see the other stations that we have within the network, but in this case I'm just displaying the coverage for these stations. So you can see here, just by the nature of the coverage, that we're using up a high resolution data. So you can see here we've got obviously some obstructions that are in the way here. And as I obviously zoom in back to layer 15 with the terrain layer on, you'll see some of the obstructions that are along the path. So whether that's trees, buildings, that sort of thing. Okay, so that's running say a coverage prediction with the high resolution data with the 1812, just to show you as a comparative for a low resolution. So I've got one that I've predicted previously just for the area, but for all of these stations. But you'll get an idea, just obviously the extra level of detail that we're getting in terms of the coverage predictions. So my previous predictions are listed under here. So firstly, I'm going to just show you the extent of all of those stations. So again, this is predicted with the high resolution, so this Lidar data. So you can see here, this is for all the stations within the network. Again, you can see this kind of almost spiky nature, just as a result of the obstructions that are in the way. If I now switch that over to the calculation that I've done on what I've called this low res, so this is this medium resolution cartography, but it's not taking into account obviously trees and buildings, etc. It's just purely a terrain-driven coverage-based. So you can see here it's a lot more uniform in terms of the prediction. We're not getting a number of these obstructions that we had, trees, buildings that are obviously included. So you can see here instantly there's quite a difference in terms of the predictions that we're getting here. So the advantage of the Lidar data is it will give us particularly for these types of frequencies, a little bit more certainty in terms of the coverages that we're predicting. But obviously, if you don't have that available for an area, then you can obviously drop back to this medium resolution data, which say we've got data for that's included for pretty much the whole of the globe at sort of 30-meter data. Okay, so that was just looking at Lidar data and a coverage example using the 1812 application model. In terms of the coverage that I've got here, so I'm going to look at a batch coverage for a number of these stations. So there's a number of ways I can do that, but if I just, for example, select the top station on the list and again run this path loss matrix. And this is particularly useful when you've got a much larger network with a series of stations that would really extend across the 100 or so that you can select in a single instance from the page via the web browser. So I've got this option down here to actually say apply to selected objects, or I can say apply to all objects. So providing I've selected just one within the list, then I can select all those objects within the network. Okay, so I'm going to run the path matrix, loss matrix calculation for all of these elements within the network, just to show you that in a batch capability. What I'm also going to do as a little aside is just show you the kind of multi-core aspect at the same time as well. So Spectrum is able to handle genuinely multi-core, so that depending on how many, in my case, I'm going to have 4 different processors that I can use on my machine. But if you've got a high availability server or something you're running, or high performance, then you could potentially have more than that. And we also have on our main, for those that are using the version in the cloud, we've upgraded recently the server capabilities, so that's in terms of speed and the number of processors that are there now. So should see some benefits for that. Okay, so I'm going to just put up my task manager just to show you this sort of multi-core functionality, and I'm just going to kick off this process running. So this is now what you'll see here. There's a number of instances of this that are running within. So this run prop mod is running here, and provided it needs, in other words, the number of instances of the core that it will run, then we can get a number of instances of that run prop mod. So let me just, perhaps a little bit quick actually, let me just select all these and I'll just increase the distance a little bit. Okay, so you can see here, so I've got these 4 instances of the run prop mod. So this is the engine that's running the coverage calculation here. So that's basically running those. When it's cleared that down, you can see it's obviously disappearing. And then if there's still a number of stations left in the network to run the coverage for, then it's popping these up as an additional process. So just to show you really that's kind of genuinely multi-core, that's being spread across, and certainly if you've got a high performance server, you'll get a significant benefit in terms of the speed and the performance that's running on. Okay, so that was in this case out to 10 kilometers. You'll see here this path loss matrix for all the stations within the network, but again, it's it's relatively quick based on the performance of Spectrum E. Okay, so the last bit for things that I was going to cover was then just to say, okay, well we've run these coverage predictions. In this case, it was using the high resolution data, and we want to actually then export this out to use it in a couple of different ways. Now, the first way I'm going to look at is called exporting to Google Earth. So this is going to generate a KMZ file. And you can see here, then we've got these predictions. So these are the predictions that I've got available. So in this case, I'm selecting the one which had all of those stations using this high resolution example. And then it's going to generate a KMZ here. So I'm just going to save that. So it doesn't have to be Google Earth that you're opening this up in. It could be anything else that will read a KMZ, but it does allow you to actually export a coverage and kind of transfer it across to somebody else. Perhaps it doesn't have Spectrum E, and then view the coverage as I'm doing here, just within the application. In this case, it's Google Earth. Okay, so you can see here that this is the coverage that we've exported across. Just a little point to note, if you want to bring in, you'll see here that the results here that we've got is just purely the Spectrum E result. If you wanted to bring over sort of the positions of the stations, then that's possible to do that as well. In that case, then if you actually select the stations before you do this export, so that will then bring over the coverage and also the names of the stations, so effectively the push pin plus the name. So just a little tip there if you want to bring that over at the same time as the coverage. In the case here where I didn't select any of these in advance, then I've purely got just the coverage, which I say in a lot of cases is perhaps the most appropriate. But depending on what you select in terms of the stations, then that will move across. Okay, so that's running just with the KMZ. In this case in Google Earth. Last one I'm just going to show then is just the other option, which is predictions to shapefile. So I'll take over just a different prediction in this case. So similar idea, select the prediction we're interested in. Difference here is then we've got a threshold that we're going to input. So I'm just putting a threshold here. You can see perhaps in the title of this, it's a dBm, so this is going to be reference to a dBm. If it was a dB microvolts per meter, obviously then it would be a different threshold you'd be putting in here, typically positive rather than negative in that case. Okay, so again, I'm just going to save this. And then having exported this, I'm just going to bring up another application here just to view the data. So I've got this shapefile which I'm just going to drag in. So this is just global mapper, and here you can see. So this is kind of a vectorizing effect in this case. So this is looking at the result with the shapefile here. So you can see this is the kind of resulting coverage map that we've got. So two potential options there for you in terms of actually looking to export coverage out. So either the export for Google Earth gives you a KMZ, or we've got this prediction to shapefile.
Okay, that's it for me.
So I'll hand over to Ross. Sarah, was there any questions before on my before I hand it over?
Yeah, Paul, before we move forward, we did have a question come in from David. Can I view coverage in 3D?
Can you view coverage in 3D? Yes.
Okay,
so let me just view one of the predictions that we had previously.
If we do have any further questions, perhaps put them into the questions toolbar and I'll be able to put them to Paul directly.
Okay, so
I'll just zoom in on the little area down here that's within the coverage prediction. And what you may see, I'm generally zooming in and out using the coverage or using the scroll wheel. The other option is to have these zoom in and zoom out buttons, or I've got this option for 3D down here as well. Now you can see this is not so interesting at this zoom level. You can see here the coverage prediction. If I move it now to level 15, so if you remember, this is the one you can start to see the high level resolution data that's coming in, and then hit 3D. Okay, so you can see here then we've got this, if I just sort of move around in that, see a lot of here was a series of trees and buildings and structures, so you can kind of get a sense for the kind of movement through angle down of these structures. So that's just a way of rendering it. Obviously, if you've got the high resolution data, then zoom into the sort of level 15 before you use this, otherwise you'll be in that medium resolution data when it's rendering that.
That's great. Thanks for that, Paul. Any other questions, please do drop them into the toolbar or put your hand up. We're going to switch over now to Ross, who's going to continue with our presentation. Over to you, Ross.
Yep, thanks very much, Sarah. Paul, just to confirm you can hear me okay and see my screen?
We can hear you great, and the screen's there. Thanks for that.
Perfect. So yeah, today, thanks very much. And I'll get started with looking at the population coverage analysis. So for this example, I thought I'd have a look at a kind of LP1 type scenario, planning that, looking for coverage percentage relating to population with covered polygons feature, and a couple of other analysis that can be done that would help in the various network planning. So this has also got applications in broadcast, where we're looking at a population coverage against a vector data set as well. So as we go through, I'll show a couple of examples. So the area that we'll be starting is the same terrain data that Paul was using. So we're looking at this Lidar function. So I thought it'd be interesting just to start from scratch, show how to input the sites and go from there. So what we'll do is I've prepared a CSV file with the network that we're going to import. So we've got a number of sites, and we're just going to import those as the TXRX object. So once these are in, we can just check that all the fields that we're interested in have came through correctly. And what I've also done is added the display radius, so that will show a circle of 0.5 kilometers in this instance around each of the sites. So I'm just checking the other details. That looks okay. So just to view what we've imported in the map, just to get an idea. So we've got these sites here in a kind of sort of cellular structure. And what we're interested in is looking at providing coverage for this kind of low power network And one of the other things that certainly within this sort of space, looking at geolocation applications that we can run. So generally those would look at having a certain receive level covered by generally 3 or more stations. So that's one of the other analysis that we'll be looking at in our downlink overlap count analysis. So the first thing that we'll do is we'll just select these and we'll run the coverage matrix to calculate our, so we'll just go out 1 kilometer here and we'll use the high resolution data set as well. Just for speed, we'll lower this for this one. We're interested in all objects. So we'll run the path loss matrix and then we'll look at doing a talk out power received so we can see the combined coverage from all the sites within our network. So as Paul mentioned earlier, we've improved our server online, so the calculations are a lot faster. Today I'm running from my local host. This is my local install on my laptop. So this should take, I think, just over a minute. Previously ran this. Maybe taking a bit longer than planned with the live demo, but we should get there shortly. So just in the meantime, I'll point out the features that we'll be using today. So first of all, we'll be using our DBM talk out power received. So that look at the combined coverage for any stations that are selected. We'll also be looking at the DBM talk out best server to identify the strongest serving station for a particular point on the map. The downlink overlap count. So that will be looking at identifying the number of stations that have a signal strength greater than a set threshold. And finally, we'll be looking at the covered polygon function as well. So we'll be importing a vector layer to the map and then identifying, compared to that, what percentage of each of the polygons within that vector layer are covered.
Ross, we have had a quick question come in. What's the relation between the profile sampling and the resolution clutter?
Right, yep. So the profile sampling and the resolution clutter are, I guess, unrelated. The clutter that's chosen here, so that looks at either the low resolution or kind of standard 30 meter data set, or the high resolution looks at any Lidar data, generally level 15 or below, that we've got loaded. The profile sampling is the number of points within the radial distance that we set. So for this one, we set 1 kilometer. So that would, for each, I believe the maximum radial, we would take 500 different sampling points within that for the coverage process. So the higher sampling, the sort of the greater detail that we'll see within the coverage once we view it on the map. So maybe to just that's it, the coverage finished now. I'll maybe do this talk out power received, and we're just looking at the composite coverage of all the sites. So here we have our kind of city centre. You can see the sort of canyon effect down some of the main roads. All these transmitter sites are just slightly higher than the buildings nearby. So generally we get this effect. So so with that sampling question, generally the higher resolution of the sampling, we'll see sort of finer detail as we zoom into the higher levels of the zoom level within our map. So now we've got the combined coverage. We've set a legend here just for a couple of different signal levels so we can view how that changes. So initially we'll look at the downlink overlap count function. So this identifies how many stations can be seen at a certain threshold level. So we look at the downlink overlap count. And again, what we're interested in is how many stations at each location can have a threshold greater than negative 110 dBm. So if we run this, now that the path loss matrix is calculated, any of the further analysis that we do generally runs pretty quickly. So we'll select the map, and now what we can see is we've got our dot palette, which can be seen by the postfix at the end of the coverage map, prediction map. And what we'll do is we'll change this to the downlink overlap palette. So what we're interested in here is if a location has 3 or more sites at negative 110 dBm, we'll turn it green. So then we could use perhaps our geolocation applications in these locations. This can be used to design network, getting some feedback on that. So if we update the palette, we should see the areas where there's 3 or more sites that can be seen at our prediction level. So generally there's reasonable coverage. Obviously some sites with 1 and 2 in the center area here. So then we would look at changing the structure and location of the sites to improve on that with the next iteration. So that's our downlink overlap count. The next one we'll look at is the best server function. So again, similar process, we'll select the sites and we'll look at a dB talk out best server function. So again, we'll set the threshold the same, and we'll put in 8 sites I think we have, and apply to the selected objects. Once again, we can see that this is a dot palette, and what we'll do is we'll just change the palette that I've prepared to the best server. So this just identifies each individual station as a different color, so we can identify what station is the best server for each location. So here we can see the strongest signal strength for each location, for each server here, coming out of it. So that's a couple of the initial predictions that we can do. I'll just unselect those at the moment. So our next topic that I'll be covering today is looking at the covered polygons. So for that, the first thing that we're going to do is upload to Spectrum-E a polygon file. So the polygon file that I've got is so data set. So this is for the area around. It's the ward areas. So in the UK, the kind of districts, council areas are split up into with different names. So what we'll do here is we'll just select the required shape files, or KML files as well can be imported at this stage. We'll open that and load it up. So we've loaded it up here. We'll maybe just change color, update that, and then we can see, as we zoom out, we can see the polygons that we've imported. So this polygon data set that we have has a population associated with each polygon. So this can be used to identify what percentage of each polygon is covered to a certain level, and then from that we would have a population count as well associated with each polygon that we can infer the population reached by maybe a broadcast station, or in this case the percentage of these stations that are covering the various polygons around. So just as an aside, when Paul was talking about exporting the shape files earlier, These shapefiles could then be re-imported with maybe the composite coverage of a network footprint, and then that could be compared to maybe a new network design going on top and looking at what percentage of the new network design kind of meets or fulfills, effectively asking the question, is this new network design going to give the same or less coverage than the previous network design that we modeled? So just as a side, that's another kind of analysis that could be done in this way. So now we've got the polygons imported. What we'll look at doing is again selecting our stations. In fact, for this one, we don't have to select the stations. We just have to have a composite coverage prepared already through the process that we did earlier. We'll select the covered polygons and it will ask us what vector layer do we want to use. So that's that one we just imported. It will ask us what prediction that we're comparing that against. And that will be our composite coverage. Again, we'll look at the threshold, and the units for this area here are taken from, again, the postfix of what type of prediction that we're comparing it to. So if we've done a prediction in dBU, maybe more used in the broadcast world, we would just identify the prediction type and then use that as the units for the threshold that we're setting here. So we'll process that, and the results that we get, we'll see, we'll just sort it by percentage. So to negative 110 dBm, this region here, this vector, is covered 98%. And as we go down, we can see the different percentages that, and we can see here the population count as well. So just when you're making up any vector files, as long as you've got the fields that you're interested in, that will get imported with the additional vector data as well that you're importing as the database behind it. From here, there's two downloads that we can have. So our first one is a XML file of the results. So that can be seen here. Again, just with the percentage, and depending on the further analysis that you're doing, you might prefer to have the CSV file, and again, that's just opens up in a format similar to the output that you can see on screen at the moment as well. So that can be again used for further analysis and reporting. So that's all with the kind of our quick view into some of the different analysis and the covered polygon functions that we can do within SpectrumE. So maybe now's a good time to just pause, and if there's any questions before I move on to the API.
Thank you, Ross. We do have a couple of questions that have come in. Can the downlink overlap count and the best server be exported to Google Earth?
Right, yep. So with the predictions, any predictions that we do, we can export them to Google Earth. And again, that's just selecting the particular prediction. So say for instance the best server prediction, we would just when we choose a prediction, the best server one, can process that, and again that will just open up in Google Earth or whatever you're using for opening your KMZ files, and similar for shape files as well, that would be loaded up. Come here. Again, as Paul mentioned earlier, since I had the points selected, we can see the call signs for each of these points as well as pins on the map, and showing the information about those sites as well. Hope that answers the question.
That's great, thanks for that. Okay, in absence of any furthers, perhaps you can move on to the next session, the next subject. If we've got any further questions, do drop them into that toolbar, and we can always pick them up at the end. Thanks, Ross.
Yep, certainly, thanks, Sarah. So the next topic that I'll be covering is a very high-level view of the API functionality within SpectrumE. So we have, again, as hosted on the server or on a local host, SpectrumE runs as a kind of client-server application. And one of the API has been kind of developed and documented to allow users to create their own applications using the Spectrum E engine. So that allows integrations with either client or customer websites to maybe have customer-facing websites that use some of the Spectrum E functionality in terms of coverage studies or path profile studies, and also allows sort of a more automated way if you want to create your own scripts to go through a high number or high volume of calls to the API and pulling back the data and then being able to edit it and manipulate it in a way that you see fit. So the API documentation within Spectrum E is located within the documentation, function tables. We've got a list of the functions here, and particularly what we'll be covering today is the API reference. So, so for any developer, the API will kind of look familiar in the kind of structure of it, sort of standard inputs and outputs effectively for each of the functions that we have. So I'll do a quick demo just to show kind of how it works, and we have a couple of sample, depending on the language that we're using, how to prepare a call to the API, and then how to evaluate the results as well, so there's more information there. So for the example today, we'll be looking at two functions. So the first one that we'll be looking at is the object edit link, which is down here. So what this does is, for a microwave link at A end and B end, it allows us to call the API to make a change to our network and make a change to that link specifically. So changing some of the parameters within that microwave link just by sending a message to the API. And the other one that we'll be looking at is doing a path loss calculation. So that effectively is the outputs from a path profile function. So we'll be choosing just get that up, choosing the model that we're interested in using. So we've got various models that we can use and setting the other parameters, and then receiving back the information about that path in terms of the parameters for the links up at the top, the free space loss, and then the receive signal strength. So for there, we can look at the effect of changing the location of a link and how that affects the free space loss. So to get started with the API, you need a developer token. So that's what generally one of the inputs. Your user email address and access token. So that's just the authentication to access the API. And you can get that by getting in touch with Spectrum Center support. So for this example, I've got another network set up just for the API test on my PC. So this is just quite a simple one. It just consists of one microwave link. I'll view that on the map. So here I've put a marker at the initial location of the A end, and that's what we'll be moving through the example. And I'll put this up here just to see what we've got. So the software that I'll be using for calling the API is a piece of software called Postman. So it's a nice piece of software for working with APIs and being able to input parameters and call various things. So the first call that we'll be doing, so we'll be posting. So here we can see just how this is broken down. So we've got our local host, which is where the server's running. So this can also be the spectrum.center website where the online version, the cloud version is located. So we're calling the server, and then the parameters, key value pairs that we're sending to it. We have the function, which is the object edit link. I've got my user authentication information here. So these are set as variables within Postman on my admin local account. We're interested in the network that we're identifying, the object that we're interested in. The UID is the unique identifier of the object. So where we would get that is within our network. The UID is located as one of the values within the object. And for this script, what I'm doing is changing the location of the latitude A variable, leaving these the same. So I can either unselect these to make no change or just ensure that they're maintaining the same values. And these are some of the other parameters that we can change as well. So we're within Postman, we can select or deselect those, and that would just add it to the parameter or the argument that we're sending to the call. So I'll just move this over to the side, set it up with Spectrum E, just so we can see the changes happening within the network. So what I'll do here is I'll send this change. Also, just within this short script here, what I'm doing is just changing the value of lat A, just to move it vertically up 0.005 of a degree every time that the script's run. So we send this. Just underneath, we'll get the send and request screen, and then we get the response from the server. And for this call, this is a correct response to say, yep, that's worked, there's been no problems. So what we should see if we move this and refresh it is that our test points moved up on the map from the initial point. So this can be made into a kind of program to either pull this data back if maybe a user makes changes through another portal, or can be used in a loop to move a site or change a parameter, maybe change the antenna height, send that to the server to update it, and then run a path loss calculation to understand the effect of changing these parameters on the objects. So it kind of opens up a variety of additional applications, I guess, that can be created using the API. So I can just send this again. What we'll see is it's just moved up again. So what we're interested in now is looking at the path loss of this object. So again, the path loss within the API documentation. This shows what variables and arguments are required and how to change them. So we're looking at the Longley Rice model here. We've set a clutter variable to 1, so we'll be able to see within the parameters in the API what that's doing. And again, in a similar manner, we would just send this to the server. And here we get a slightly more detailed response of the parameters about the site that we're interested in, and then the receive signal level from this link, kind of A and B direction. So we can see that at the moment it's -159. What we can do is we can move our link up. You can see that's moved, and then if we recalculate this, we can see that that's changed for the new link that we're doing. So again, all this gives developers and our clients the tools to really create their own kind of automated analysis and pulling data back using the API tools. So that's a very quick introduction. As I said earlier, if you would like to start using the API, please get in touch. And I'll maybe leave it there for just now and see if there's any questions. Thanks very much for joining us.
Lovely, thanks for that, Ross. We have got a quick poll that we'd ask everyone just to have a quick vote on. So this will just help us understand whether there is any requirement within your organisation for the API. Ross, while I've got you here, we did have a question that did ping up from that. What object types are coverage calculations returned in? So that's what object types are coverage calculations returned in.
Cool. So, so we can look at the API call for coverage. So I think it's a get coverage. So I believe it's KMZ and grid ASCII that we can return coverages in. So yep, so we've got object type, so it should be a when we request it here. Yeah, so we can get KMZ, ASCII, or the combined, both the KMZ and the ASCII file. So then the returns information here will tell us how that's presented to us when we when it's returned, and then again we just set up the correct code within our program to manage that as well.
That's great.
So maybe that could be integrated into a website where the call's made when a customer asks for maybe what's the broadband prediction in my area, and that's returned, or certainly there's many different options for applications that can be made as to how much detail you want to show as well. So there's certainly lots of options there certainly with KMZ and the ASCII formats, depending on what your application is.
That's lovely. Thanks for that, Ross. We have got some questions coming in now. If you do have a question, you can either put your hand up or you can drop a question through the toolbar. If you put your hand up, I can open you up with your mic and you can talk directly to the presenters. We've got a couple that we'll kick off with. Please do feel to ask questions. Okay, so the first question, the difference between tree obstructions in winter with no leaves and spring, is it possible by just changing the path loss? Paul.
Okay.
So just to
cover
muted
a little bit. So, I mean, generally, the example we look at here was with Lidar data, and I guess it depends. First is what's captured at the original time that the data is collected. Typically, they're done in kind of autumn, winter time. Certainly for the ones that I've seen. So over here, that's kind of in the UK, that would be sort of running this time of year. Certainly the ones that we looked at in the example based on the Environment Agency data, I think they survey between about October, November through to April. So I guess during that time you would potentially not have all of the leaf out on the trees. So you would get some variation in terms of the attenuations as a result of having full foliage and not, or somewhere in between those. But I guess if let's say the Lidar example here predominantly taken when the leaves are off the trees, then you may want to just add in an additional margin. So when working out, for example, link budget, so trying to determine a planning threshold. So let's say we were working down, in the case that I had, to -90 dBm, you may want to add a little margin in, say an extra 3 dBs, for example. So suddenly, instead of that -90, your planning threshold might go up to -87, for example. So I can say it would depend on the data sets, but if you know when they're captured, then obviously you can make a judgment as to whether they're likely to be full leaf or not. And then typically, if it's not including those, then applying some sort of additional planning margin is probably a sensible way to do it.
Unmuted.
Thanks for that, Paul. That's great. Okay, the next question is for Ross. Ross, it's regarding the API function, the object get link function within the API. If elevation A or elevation B are below actual terrain ground level, how is the path loss calculated? So that's whether elevation A or elevation B are below the actual terrain ground level, how is the path loss calculated?
Right, so I'm not that familiar with the API myself, so I think that's one if you can make a note of that, Sarah, we'll get back to customer on that one.
Perfect. Okay. we have a couple of questions that have come in that are personal to customers' use, so we're going to skip on that at the moment. There are a couple of things I wanted to follow up while we wait for a few more questions to come in. We'll follow to today's event with a survey. We ask everyone if you could just take 2 minutes of your time to complete that survey. That feedback goes back into the webinar user group machine, and it helps us develop future events for you. I will be sending you a follow-up email from today's events. That email will include an invite for our up-and-coming webinar, which is due to be held on the 6th of February. Our next webinar will be on ITU R1617 and the implementation into Spectrum E. And that will be modelling and calculating diffraction and troposcatter links. So details of that will be available, and an early bird invitation will come in that email. We'll also be recording today's event, and a link for the recording will be available for you too. Okay, so lastly, the other thing I was going to cover was any access to any documents that needed that cover some of the subjects we've covered today. So all of the documentation, particularly the Getting Started guide and a guide to the API are available via the Spectrum Centre portal. So please do, I think Ross is showing you there that the whereabouts these are all available for. Please do access them. If you have any further questions about any of the subjects that have been covered in today's event, by all means reach out to us and we will help them. Okay, so just a couple more questions. This one is about best server display. How does one correlate sites versus display?
Right. Yep. So, the best server function, the documentation here identifies the kind of process for setting the sites up, how you change the parameters within the sites to correlate to a certain color within the setup of the display there. So this document here is the best one for that.
That's great. Thanks for that, Ross. Okay, next question. Is the downlink simulcast available to everyone?
So I maybe need to get back on that one. Sometimes it's just a case of within the user account just enabling it. I guess it would depend possibly what subscription you're on. So if you leave that one with us, we can get back to you on that.
That's lovely. All right, and just one last one that we'll be able to take today, and that's about Lidar data availability. I know you mentioned earlier that there was Lidar available for certain parts of the world. Perhaps you could specify whereabouts that is covered.
Yep, so certainly within the UK, there's a DEFRA website. They've got access to some of the open data for the entire of England. For Scotland, I believe it's the SEPA website that hosts it. But if you type in Lidar data UK, you usually get the links to it. If you can't find it, please get in touch and we'll send you the links as well on that one. For the rest of the world, there's some countries, depends specifically the country, some have open data sets similar to the UK. Other ones, there's private companies that provide Lidar data, so you can either contact them directly or we can help you out on that behalf and get the data set imported to Spectrum E for you as well.
That's great. Thank you, Ross. Just one very quick question. Is there a limit to the number of site sectors for best server?
So I guess probably the limitation would be in terms of the palette size. So the kind of coverage area. Certainly having multiple sectors in the same site. I guess once you get to sort of 30, 40, it might be quite challenging to, partly with the repetition of colours. That's the only kind of limitation I can see straight away. But we'd have to look a bit further at the specific example to identify any other limitations there.